Hi and welcome. I've been working with the Math.Big package in the Go programming language, mostly with floats, and I have a couple things to talk about with respect to how to use them. Before I get started, I should note that I work for Google, but this is a personal project, so all the views, opinions, and everything else is mine, and everything here is going to be an Apache 2 license. So Math.Big, why would you use it? The reason you use it is when you want to get an arbitrary precision on some number. So if you need to get something that your 64-bit float won't handle or a 64-bit integer won't handle, you can use Math.Big and get up to an arbitrary precision. So how this works is we are going to specify some precision. So here I'm saying I have a 6,000 byte precision as opposed to a 64 byte precision. And I just picked this number because it was high, but for this, we don't quite need 6,000 bytes. And then I'm going to define a new float. I'll set the precision, and here I'm setting it as an integer. So this is 1.0, it's a float at 1.0 to 6,000 bits. The example I'm going to show is if I raise 1/2 to some high power, what happens? So I am making a new float, setting it to 1. I'm also making a new float and setting it to 2. And then I can do a division with base, with my big float, and then QUO, which is a little counterintuitive to me, but that means quotient. That's standing for quotient. So here I'm going to do a division, 1 divided by 2, and this base is now 0.5 with 6,000 bits of precision. And then I want to take to the power of 100. So I'm defining 100 in N64. And then I have a function that I've made which will do this exponent. But first, what happens, this does this exponent in a big float friendly kind of way. But I've also here have a float 64 that I've done. So here just math pow. If I take 0.5 to the 100th power with float 64, what would I expect to see? So I'm printing these out. Here I am converting this result in big float to a string with 100 decimals so that it'll print out in a way that's nice for us. So when I run this, I see that my big float, I get it to the 100th power, it's a bunch of zeros, and it's 788,609. And actually I get the same thing with my float 64. And that turns out to not be a surprise, although I was slightly surprised when I saw it, but it's not really a surprise because the float 64 is only starting its precision at here. So it has 64 bits of precision, but it starts here, so it doesn't keep all these leading zeros. So I can make it, I can make the float 64 drop all these extra numbers that it has, 64 bits of precision, if I put a number here at the front. So let's say I have this result. I have my result from my big exponent, and I have my result from my float 64. And let's say I add 1 to them. So here I am doing the big way of addition. So just like I had my quotient for a division, I have add result to 1. I'll convert that to a string. And now I get my big value. It should be, we expected this to be 1 point, a whole bunch of zeros, and then 788. And I do the same thing with my float 64. If I just add 1 to it, and then I print those out, then what do I get? So this is the results we saw before. And with my big power, with my big numbers, I get 1 point, a whole bunch of zeros, and my 788. Basically, it's exactly this plus 1. My float 64, I dropped all these extra decimals. because it didn't have enough precision to keep all these zeros and then this plus the 1. I was playing around with it. I actually expected that the float 64 would have 64 bits of precision, and therefore it could handle up to 2 to the maybe 63rd power or so. But what I found is it handled it right around 50. It could keep right around 50. See, I have a 9 there in my float 64, and I have 8 there. But if I only took it to the 49th power, the precision is matching. If I take it to the, let's say, 52nd power, my float is maybe 54th power. My float is dropping. So I'm not quite sure why. I thought it might be 64, but I must be using bits for something else. So how do I know how much precision I need? So let's say I wanted to keep, 100 decimal places. Keep 100 decimal places. I need 2 to the x equals 10 to the 100 bits of precision. So whatever that is, you can do it with logarithms. It's basically 2 to the 3.3 power-ish is 10. So we would need to keep, if we wanted to keep 100 decimal places, we would need to keep 100 times something like 3.3 bits of precision. Although I believe you'd really want to keep more than that. So instead of keeping 100, you'd probably want to keep 100 times whatever the math is. I think it's log 10 to, I think 1 divided by plus some extra. If you did this math and you did a bunch of, let's say you had 100 bits of precision, and you multiplied, added, subtracted some numbers together, I'm pretty sure you would end up with less than 100 bits of precision. So I don't know that for sure, but I think you would. So I would keep more than you need. All right, so that is, how the float works, or big float works. Why did I do my big float exponential? I made this myself because, unfortunately, big float doesn't seem to have a built-in exponent. Big integers do. Like big integers, I could go exp and then get a value, but big float didn't. So I just built my own function. I'm passing a big float, the precision, a integer power to take it to, and then it does the exponential for me in log arithmetic time. So here it's a recursive function. If my power is equal to 1, if my power is equal to 0, then I'm at a base case and I just return a value of 1. If my power is equal to x, 1, then I just return x because x to the 0 power is 1, x to the 1 power is x. X to a negative power is the same as 1 divided by x, so I recurse back and just do a division here. That's what that quotient is. And otherwise, I recurse and what I'm doing here is, let's say I have x to the 11th, I end up saying x to the 5th times x to the 5th times x. That's why I cut this in half, keep a remainder, whereas x to the 12th would be x to the 6th, x to the 6th. And then multiply them together. So this is in base 2 logarithmic time, but it doesn't work with fractional exponents. So let's see, we said the big float division, addition, here is big float multiplication, subtraction is SUB. So it's nice. I am using it to try to calculate pi out to a big number of digits. And it's worked so far, but I've run into a couple stumbling blocks. Mainly because the more digits of precision you keep, the slower it goes. And it's not so bad for these things, but it's becoming a problem for me when I'm trying to push pi out to more than about 100,000 digits.